So in general, for proton NMR, which is looking at hydrogen 1 nuclei, we have a range from, it goes usually from 1 to 8, and then there's some at 9 and 10 and 11 and 12 and so forth. So, but generally between the 1 through 12, you can usually see a range of functional groups. Down here, we have signals that are more downfield. Right here, we have signals that are closer to 0. These are called upfield. This is sort of relative. Upfield is closer to 0. And then higher numbers are what we call downfield. So looking at this particular spectrum, I would say, okay, this peak signal is more downfield than this one. This one's more upfield than that one. This is more downfield than both of them. This is the most upfield signal. And so that sort of gives you an idea of how chemists picture the spectrum. We either picture things on this side or that side. Chemical shift is based on the idea of shielding and de-shielding. So I mentioned that earlier here. If there is electron density or the electron cloud is being pulled away, then the external magnet is felt more strongly. And what that does is that causes de-shielding. So this nucleus is de-shielded when the electrons are pulled away, and then it feels the magnet more strongly, and so that pushes the signal downfield. So that's where these kinds of signals are from, usually, but not always. There are other effects as well, which we'll talk about. Up here, upfield means that we're shielded, meaning that you don't have this electron cloud being pulled away. So that means that those electrons help to shield the magnetic field here. So that nucleus doesn't feel as naked, as exposed. And so that means that it's shielded. Now there are a bunch of different functional groups that have certain characteristics of how shielded their hydrogens nearby are, or de-shielded their hydrogens are. So let me show you what those are, and you should start memorizing them as soon as possible, because the fact that this is here at 7 to 8 is going to tell me a certain thing, and between 1 and 2 this is going to tell me a certain thing about what kind of structures, what kind of structural features there are in this molecule. So in this space right here, let's just draw the x-axis, and I'd like you to number it from 0 to 12. Okay, and this is chemical shift, so please show that. And the symbol for chemical shift is lowercase delta, like partial positive, partial negative, that delta, and we put ppm for its unit. So always label your axes. That's what scientists have to do. Okay. So now at 0, we usually have a reference compound called TMS, trimethylsilane, and that allows us all to calibrate our NMR, because where the actual peaks appear could be offset. Then you want to have a reference compound, which means anytime you run a sample, that reference will help you point it to 0 and set the X values properly. So that's called having a reference. Now from 0 to 2, that's where I usually see alkyl hydrogens. So I see CH. I see these kinds of H's on carbons that are bonded to other carbons. So just single bonded carbons of, boring alkanes. Those are where I see the H's. From 2 to 3, I usually see several kinds of hydrogens here. One is the alpha hydrogen of a carbonyl group. So that's a carbon attached to a carbonyl. I see a hydrogen that we call the alpha hydrogen because it's on the carbon next to the carbonyl. We also see alkynyl hydrogens here, and we also see benzylic hydrogens here. Okay, so these are always hydrogens next to carbons next to some kind of functional group. Now from 3 to 4, I usually see oxygen bonded to carbon, and then that carbon's bonded to a hydrogen. Or I see a nitrogen bonded to a carbon, which is bonded to a hydrogen. It's important to note I don't see the hydrogen on the oxygen here necessarily. I'm talking about the hydrogen on the carbons next to the oxygen or nitrogen. Also halogens. Halogens are also included in that group. So now we sort of skip around a little bit. These are approximate values, so you do see things in other ranges slightly. Like if I had a benzene ring and an oxygen, you might see an additive effect and you might see a peak out here. So just FYI, these are just guidelines. 5 to 6, I generally see alkynyl hydrogens. So like these guys, on the carbons on double bonds. Over here, 7 to 8, I see hydrogens on a benzene ring. So like that. 9 to 10, there's an aldehyde hydrogen on the carbonyl. This was the alpha hydrogen on a carbon on a carbonyl. This is now a hydrogen on the carbonyl. Okay. So as you expect, the electrons would get pulled away, de-shielding this. That's why it's at 9 instead of 2 to 3. And then our last one over here is usually where I see carboxylic acids are generally 10 and above. So I'm just going to put my carboxylic hydrogen. So right now it probably looks like a lot, but if you practice as much as you need to practice, this will become just second nature to you. Particularly important, I would probably learn aromatic ones first, because that sort of gives you a sense. I think there's an activity you're going to do where there's molecules that have the benzene ring in them and molecules that don't have the benzene ring in them, which are called aliphatic. So aromatic and aliphatic. And it's just really easy to tell because you only have to look at this range and you can already tell if it has a benzene ring or not. And then if you have carbons on the benzene ring, you may also see the benzylic signals as well. So it just gives you a nice way of telling something really important right off the bat. Sort of like how on an IR you can tell if there's a carbonyl group or not, or you can tell there's an alcohol group or not. Those are like the two easiest signals on an IR. This is one of the easiest signals on an NMR, as well as the aldehyde and the carboxylic acid, because they're the only things possible in that range. All of these over here, it's really thinned out. Here there are multiple options, makes it a little bit harder to tell. Another thing that I'll say is really important is I mentioned that there are these hydrogens on the oxygen and on the nitrogen that aren't between 3 and 4 necessarily. So where are they? They tend to be what we call exchangeable. So if I have an OH group or an NH group, you guys know that these can be proton acceptors or proton donors. So if I had another alcohol nearby, that this alcohol could grab that H, and then this O could grab someone else's H, and so you have these hydrogens moving around. So as they get bounced or tossed from one molecule to another, it becomes hard for us to read their signal because they're not permanently attached anywhere. So because of that, we generally see a variability in where they show up, and oftentimes they show up as a single peak that's sort of broad. The other peaks tend to be really skinny, like this, okay? And so these exchangeable hydrogens tend to be a little bit more broad, and they occur randomly between, let's say, 1 to 8 ppm. You usually see sort of a peak like this, corresponding to that hydrogen. And sometimes you don't see a peak at all, because if you have a deuterated solvent, let's say our deuterated solvent is this molecule, and your molecule is this. Your molecule might grab that deuterium, and then this hydrogen might get taken off by another molecule. So you actually end up with a molecule that's deuterated instead of having hydrogen 1. And then your NMR doesn't pick it up at all. So this peak sort of disappears then. So that's actually called D2O shake, is if you have a molecule with exchangeable hydrogens like alcohol groups, and you put a deuterated solvent in and they can exchange their protons, you'll start to see this peak go away or diminish in size as that exchange occurs. And that's really great, because then you can sort of show that that's the hydrogen that corresponds to a certain peak, because you'll see the peak get affected. Now you talked about how electronegative atoms nearby will pull electron density away that exposes me or the nucleus to the external field, and so that causes de-shielding or moving of the signals downfield or to higher values. Let's look at the effect of that. It starts with halogens right here. We start to see halogens, oxygen, nitrogen, our very electronegative atoms, start to move these signals down to 3 to 4. And so you can see the effect of, if you just had hydrogens, this tends to be at 1 ppm. If you add an iodine, 2.2, go more electronegative, go more electronegative, you see the trend. You see the effect of how these hydrogens feel the external magnet. As these electronegative atoms pull the electron density away, they're going to feel that magnet more. So that delta E, the resonant frequency is going to become larger. So what we'll do is we'll practice by looking at the different kinds of hydrogens in this molecule, and we're going to figure out where their chemical shift is. Just try to predict it. It's not going to be exact, but use the ranges that I provided you, and just start getting used to this. And let's also think about non-equivalent hydrogens as well when we do this. So, all right, first we've got hydrogens out here. These are methyl hydrogens, and they are on an alkane carbon, an alkyl chain. So these are going to be just my regular alkyl hydrogens, which are down here. So this is somewhere between 0 and 2. So probably around 1 ppm, or you can put the range 0 to 2. These guys here are next to a carbonyl group. So if we look at the alpha hydrogens of a carbonyl group, they're not on the carbonyl group, they're next to it, then that's going to be between 2 and 3. So I'll just put a note here. Okay, and these are equivalent to each other, so there's going to be one signal here between 2 and 3. These are equivalent to each other, so there's going to be one signal between 0 and 2, probably closer to 1. The other hydrogens I see are right here, H2 here. So these are next to an oxygen right here. So they're on a carbon next to an oxygen. So here's my carbon next to an oxygen. Here's the hydrogen. That's the one I'm looking at. So that's between 3 and 4. So this one here is going to be appear in the NMR between 3 and 4 ppm. And then these are just, this is an alkyl chain. So nothing's really special about these guys. So between 0 to 2 ppm. And so these are non-equivalent to each other. So these two hydrogens will have a different signal than these two hydrogens, but they'll be in the same range. And it's possible they'll overlap with each other and give maybe a sort of a complicated signal. All right, so go through and practice that and use your chart and start to memorize those values and get a sense of what kind of functionals groups are involved. Do you have a benzene ring? Do you have oxygens, nitrogens? Maybe it's a hydroxyl group. Maybe it's an aldehyde. Go through it and take a look. All right, so just going through some of these. These over here are between a carbonyl and an oxygen. So this oxygen would make it between 3 and 4. This would make it between 2 and 3. They would add together and maybe give us something a little bit greater than 3 to 4. Here is next to an oxygen, 3 to 4 ppm. There's no hydrogen here, so no signal here, but there are hydrogens on these methyl groups, and they're pretty far away from this oxygen, so it's going to be 1 to 2 ppm, or 0 to 2 ppm. I'm just going to say 1 to 2 ppm, but it could be 0 to 2 ppm. It could be slightly under 1. It's fine. These alpha hydrogens here are 2 to 3. The hydrogens on this alkyl chain are going to be 0 to 2, or 1 to 2. This hydrogen here is an aldehyde hydrogen, so 9 to 10. These two are alpha hydrogens to the carbonyl, so 2 to 3. These vinyl hydrogens next to an alkene are 5 to 6. These guys here are next to the alkene and the alkyne, so they might be slightly higher than 1 to 2. But 1 to 2 is fine. H is 2 to 3 because of the alkyne. These double bonded H's are 5 to 6, and these methyl ones are 1 to 2. But there's close to this one, so it might be a little bit higher. 1 to 2, same reason. This one is next to this is on a carbon, hydrogen's on a carbon. on an oxygen. So they're 3 to 4. And the hydrogen on the oxygen is the variable 1 to 8. For this last molecule, we have methyl group here 1 to 2, vinyl group 5 to 6. We have these alkyl groups 1 to 2, but the ones next to the double bond in resonance might be a little bit different, maybe a little bit higher. So we talked about de-shielding, and we talked about shielding and the effect of electronegative atoms like these on shifting the values downfield a bit. Now, why is it that we have these double bond or pi systems that shift it even more downfield? Now, you might say, or I would say, that the hybridization is different. So you have sp2 carbons here. And sp2 carbons are, in a sense, more electronegative in that they have more s characters, so the electrons come in more, right? So you might feel that the sigma bond here is now closer to this carbon because it's sp2 orbital as opposed to sp3. So when those electrons get brought in, maybe this hydrogen feels more de-shielded. Well, there's also this other effect called anisotropy, and this is really why or how we explain that effect. For benzene in particular, we talked about the shift being way down there, 7 to 8 ppm, as opposed to the alkyl groups at 0 to 1. So this is explained by an effect called anisotropy. And basically what that is when some molecules with these pi systems, like alkenes and benzene rings, when they feel that magnetic field, so you put a magnet next to a benzene ring, in the pi system of the benzene ring, so which is the double bonds here, the pi bonds, that will cause an induced magnetic field. And that magnetic field sort of looks like this. So the hydrogens here, clearly they are affected by that induced field. And what's happening is the applied magnetic field, let's say the magnitude of that field, let's say the magnitude of this field is felt this much, okay? Well, what happens here is that this hydrogen feels the induced field. So let's say there's an amount of induced field that adds to the amount of the external field, and so now it feels a field greater. So the effective field, or the field that it basically feels, is not only this, but it also feels this. And so those add up together and it feels this. And when it feels a greater field, it's like you're pulling electrons away from it. There's a kind of, it's the same effect as being de-shielded. So feeling the field greater causes it to be downfield more, 7 to 8. Now with some pi systems, that's not the case. It is with double bonds and benzene rings, but with triple bonds, they're actually still upfield quite a bit, 2 to 3. So why don't we see that there? Well, in a triple bond, we see a different kind of anisotropy. So we see anisotropy as well. For an alkyne, we see a different induced field than here. Here we see a ring current that induces a field this way. For this alkyne, we see a field that goes more like this. So it almost treats this alkyne like a cylinder, and then the induced field goes like that. Okay, so because of that, this hydrogen is not feel the same environment that the benzenes do. It's actually sort of the opposite. This hydrogen ends up having an induced field that subtracts from the external magnetic field. So it's going in the opposite direction, so it subtracts from the signal. So for example, let's say the external magnetic field is this strong, and then the induced field of this hydrogen is actually subtracting from that. So the total net field that is felt is only this much. So that's why these feel more shielded rather than more de-shielded.